So in chapter 8, lesson 3, we're going to talk about scientific notation. So we're going to learn how to express numbers in scientific notation and standard notation. We're going to find the products and quotients of numbers expressed in scientific notation. So some vocabulary to keep in mind is what is scientific notation? So scientific notation is important in astronomy because astronomers often work with very large numbers, such as the masses of planets. The mass of each planet in our solar system is given in the table. Notice that each value is written as the product of a number and power of 10. These values are written in scientific notation. So here are the values written in scientific notation. So like Mercury is written as 3.30 times 10 to the 23rd power. Well, remember 10 to the 23rd power is 10 times itself 23 times, right? 10 times 10 times 10 all the way down the line, 23 times. That's going to be a huge number, right? It's going to be a 1 with 23 zeros behind it. And if I take that and multiply by 3.3, obviously that's going to be an even bigger number, right? And so that's what scientific notation really comes into play is in mostly in science when we're dealing with such massive quantities and values. It also comes into play if we're dealing with really small values, like in biology, if I was trying to measure cells, those distances are so small that they require tons of decimal places to be able to represent them. So scientific notation is very helpful in that way. So scientific notation, when dealing with very large or very small numbers, and like I said, small numbers refer to things that require a lot of decimal places, keeping track of place value can be very difficult. So for this reason, numbers such as these are often expressed in scientific notation. So here's the first key concept. Scientific notation is a number that is expressed when it's written as a product of a factor and a power of 10. So the factor must be greater than or equal to 1 and less than 10. So for example, a times 10 to the nth power means that a, we need to be a number between 1 and 10. N is an integer, so any positive or negative whole number, right? That would be how we would write scientific notation, right? It is a factor times some power of 10. And again, the factor, that number there, needs to be a number greater than or equal to 1 and less than 10. So the following examples show one way of expressing a number that is written in scientific notation and its decimal or standard notation. Look for a relationship between the power of 10 and the position of the decimal point in standard notation of a number. So 6.59 times 10 to the fourth power can be written as 6.59 times 10,000, right? Because 10 to the fourth power is really 10 times 10 times 10 times 10, right? A 1 with 4 zeros. So if I were to write this out and calculate this, right, 6.59 times 10,000, put that in your calculator, and you would get 65,900. Now I want you to notice and make this observation. Previously, the decimal was between the 6 and the 5. So if I count how many decimal places it moved 1, 2, 3, 4 decimal places. So really, the connection between the exponent of 10 is how many decimal places to the right it moved to create it in standard notation, right? So this is scientific notation, and standard notation is a normal notation you've been using for numbers your whole life, right? It's just the standard way we write things. Let's look at one more. So I have 4.81 times 10 to the negative sixth power, right? So again, think about what we talked about in the last lesson. What do negative exponents actually mean? Negative exponents don't mean negative numbers. They refer to reciprocals. So 10 to the negative sixth power can actually be written as 1 over 10 to the sixth power. Again, if I were to calculate this out, 10 to the sixth power, right, would be a 1 with 6 zeros in it. So 1 divided by that would give me 0.00001. And if I take that decimal and multiply by 4.81, that's going to give me 0.0000481. Again, make the observation of where the decimal used to be. It used to be between the 4 and the 8. And now it has moved 1, 2, 3, 4, 5, 6 decimal places to the left, which coincides with the exponent. So this is going to bring us to the expressing our next rule, which is how to write scientific notation in standard form. So the first thing we would do is to determine the exponent, right? Is it positive or negative? If it is positive, then the decimal point is going to move to the right that number of places, right? So in this one, it was positive, it moved 4 places to the right. If your exponent is negative, right, less than 1, that means your decimal point is going to move that many places to the left, okay? And obviously, you should add zeros and a decimal point or commas where needed to make sure you indicate the appropriate place value. So again, another important thing to write down. So let's look at this first set of examples here. So we are needing to write scientific notation in standard notation, right? So we're converting numbers from scientific notation and we're going to write them in standard notation. So let's look at this first one here. Let's look at A. So 2.45 times 10 to the 8th power. So again, we're going to identify our exponent. It is positive 8, which means that's going to move our decimal point 8 place values to the right. So if I count it out, it's going to go from 2.45, again, 1, 2, 3, 4, 5, 6, 7, 8. It's going to create 245 million, right? I had a positive exponent of 8, so I moved the decimal point 8 places to the right. Now let's go ahead and look at B. Again, identify the exponent. It is a negative exponent, right? It's 10 to the negative 5th power. So currently right now, my decimal place is not visible because it's a whole number, but I know that my decimal point is right to the right of 3, just behind the 3 there. And again, if I were to move the decimal point, it's going to move to the left 5 places. So that's going to mean that it's going to move from here. It's going to move 1, 2, 3, 4, 5 places to the left, since it had an exponent of -5. Because again, negative exponents represent very small values, and positive exponents represent very large values. And this is a perfect example of those two things. So if I wanted to express a number in scientific notation from standard notation, I would just reverse this process, right? So let's go ahead and take a look at that. If I were to reverse this process, I would use the following steps. First, I would move the decimal point so it is to the right of the first non-zero digit, which would result in a value between 1 and 10. And I would make the observation of how many decimal places I moved the decimal point and what direction I moved it in. And that would tell me what my exponent would be, right? So remember that the A value needs to be between 1 and 10. And the exponent is the number of place values you moved it. If you had moved the decimal point to the left, it would be a positive exponent. If you had moved the decimal point to the right, it would be a negative exponent because, again, positive exponents represent very large numbers and negative exponents represent very small numbers. Let's go ahead and take a look at these examples. So here, the numbers are presented in standard form or standard notation, and we're going to go ahead and convert these to scientific notation. So here I have 30,500,000. So again, remember the decimal point is at the very end here, right behind the 0. And I'm going to move the decimal to the left to create a number between 1 and 0. So I'm going to move it to the left to right in between the 3 and the 0 there, and it's going to create the number 3.05. That is a number between 1 and 10. So if I move that decimal place, that means I'm going to move it 1, 2, 3, 4, 5, 6, 7 places to the left, right? So now I know that my exponent, my power, has to be 7. And it needs to be positive 7 because I moved it to the left, and I'm representing a very large value, right? So my scientific notation number would be 3.05 times 10 to the 7th power. I know I did this correctly because this is a number between 1 and 10. And this is representative of how many decimal places I moved it in what direction. Let's look at B now. So 0.000781. So this is a very small value. So in my head, I'm going to make a mental note that I know this is going to be a negative exponent. So now I need to figure out how many decimal places it moves. It's going to move to the right, and it's going to move right in between the 7 and the 8 because I need to have a value between 1 and 10. So it's going to move 1, 2, 3, 4 places. So it's going to be 7.81. And since I moved it 4 places to the right, it's going to be 7.81 times 10 to the negative fourth power. Again, recognizing that it's a negative exponent because it does represent a very small value. So a little tip to remember is if you notice in scientific notation, I always have one digit to the left of the decimal point, right? Notice my one digit is 3 here. My one digit is 7 there. There's always one digit to the left of the decimal point in scientific notation. You're often going to see very large numbers in the media written using a combination of a number and a word, such as 3.2 million. To write this number in standard notation, you would rewrite the word million as 10 to the sixth power. The exponent 6 indicates that the decimal point should be moved 6 places to the left. And if you remember, the reason why it's 10 to the sixth power is because 1 million is 1 with 6 zeros after it, right? So if I look at 3.2 million, it would be written as 3,200,000, right? It would just be taking the decimal point and moving it 6 decimal places to the right. So let's look at an example here. This graph to the right shows chocolate and candy cane sales and total candy sales for a recent holiday season. So we need to go ahead and express all the values of these sales in standard notation and then write those same numbers into scientific notation. So let's go ahead and start with the candy cane sales. So 120 million, remember a million represents 10 to the sixth power. So I need to move the value 6 places to the right. The decimal point 6 places to the right creates this number in standard notation. And now I'm going to look at 300 million. Again, million represents 10 to the sixth power. So it's going to move the decimal point 6 places to the right, which creates this number in standard notation. And 1.45 billion. Now, if million is 10 to the sixth power because it's got 6 zeros, billion is 1 with 9 zeros. So it's going to be 10 to the ninth power. So this is going to move the decimal 9 places to the right. So again, if I have 1.45, I'm going to move it 9 places to the right, which would create this value right here, $1,450,000,000. That's a lot of money. All right. So now we're going to go ahead and convert these values into scientific notation. So right now, if I look at candy cane sales, the decimal point is just behind this last zero here, just the right here. I'm going to move the decimal to the left. And remember, it's got to create a number between 1 and 10. So I'm going to move it right in between the 1 and the 2. So I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8 places. So that's going to create 1.2 times 10 to the positive 8th power. It is a positive exponent because it's being representing a very large value. Let's go to chocolates now. Again, here's the decimal place just to the right of the 0. I'm going to move it to the left 1, 2, 3, 4, 5, 6, 7, 8 places. So it's going to be 3.0 times 10 to the 8th power. Again, 3.0 is a number between 1 and 10. Let's look at the all candy value, right? So again, here's the decimal place. I'm going to move it to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it creates 1.45 times 10 to the ninth power, right? I moved it 9 places to the left to create a number between 1 and 10. 1.45 is between 1 and 10. So these are the values written in standard notation and scientific notation. So products and quotients with scientific notation. You can use scientific notation to simplify computation with very large and very small values. So in example number 4, we're going to go ahead and multiply these two scientific notation numbers, right? And we have to express them in scientific and standard notation. So if I were to take these values, I could regroup them. So I group just the numbers together, right? 5.5 times 2.9. And I can group the two factors of 10 together, 10 to the negative 8th times 10 to the second. Now 5 and 2.9, right? I can do this, right, because I can use the commutative and associative property, right? I can regroup things and do them in different orders because it's multiplication, right? Multiplication can be done in different orders, right? 3 times 4, 4 times 3, they mean the same thing, right? They both equal 12. So this is what allows me to regroup them. Now I regroup them because I can do 5 times 2.9. Those are just two numbers being multiplied together, right? Maybe you don't know off the top of your head, but you can use a calculator, and it gives you 14.5. 10 to the negative eighth times 10 to the second, that we can use our exponent rules, right, from lesson 1. 10 to the negative eighth times 10 to the second, same base, add their exponents. Negative 8 plus 2 is negative 6. Now, this is where some people run into trouble. They think that they're done because it's in scientific notation, but you remember one of the requirements for scientific notation is that this value in front, this factor here, needs to be between 1 and 10. Right now, it's bigger than 10. 14.5 is too large, so I need to move the decimal place one value to the left. So I'm going to write 14.5 as 1.45 times 10 to the first, right? And someone might say, why did you rewrite it like that? Well, if I take 1.45 and multiply it by 10, that gives me 14.5, right? These two things are equivalent to each other. But the main reason is I need this value to be between 1 and 10. So now it is. 1.45 does fall in the middle or in between 1 and 10. Now, again, I can use my associative property to regroup this. So the 10, the factors of 10 are multiplying, right? So 10 to the first power times 10 to the negative sixth power. I can use my my product of power rule, right? I can go ahead and, since they both have a base of 10, I can add their exponents. 1 plus negative 6 is negative 5. So it gives me 1.45 times 10 to the negative fifth power. And then to write it into standard notation, again, negative exponents are representative of very small values. So I know that I need to move my decimal point to the left 5 places. So it's going to be, in standard notation, it's going to be written as 0.0000145. So now I've concluded, I've represented my value in scientific notation and in standard notation. Now that we've dealt with multiplication, let's look at division. So in division, right, a quotient, they want us to evaluate 1.2789 times 10 to the ninth power over 5.22 times 10 to the fifth power. And they want us to express this result in scientific and standard notation. So 1.2789 times 10 to the ninth power over 5.22 times 10 to the fifth power. Again, similar strategy as before. I can regroup them, right, using the associative property. I can group the two numbers together, right? 1.2789 over 5.22 and 10 to the ninth power over 10 to the fifth power. So again, how do I simplify this? Well, this I can just put in my calculator, right? 1.2789 divided by 5.22. And over here, I can just apply my exponent rules, right? They have the same base, 10 to the ninth over 10 to the fifth. Subtract the exponents. 9 minus 5 is going to give me 4. So now I have 0.245 times 10 to the fourth power. So again, we want to identify that this value out in front is not between 1 and 10, so it's not quite in scientific notation yet. So again, I need this decimal to be between the 2 and the 4. So I need it to be 2.45. So I'm going to rewrite this in scientific notation, right? So 2.45 times 10 to the negative first, which is like dividing by 10, would be what would be equivalent to this, right? So these two things in red are equivalent to each other. But now it is a value between 1 and 10, right? 2.45 falls between 1 and 10. Now I'm going to use the associative property to regroup this so I can have the two factors of 10 next to each other, right? 10 to the negative first times 10 to the fourth power. Again, add their exponents because they have the same base. Negative 1 plus 4 is 3. So I'm left with 2.45 times 10 to the third power. That is scientific notation. So now I can go ahead and convert it to standard notation. It's a positive exponent, which means it represents a very large value. So it's going to move it 3 places to the right and give me 2,450. So that's how I'm going to go ahead and use my knowledge of exponent rules and scientific notation to be able to not only multiply values, but divide values. That's the end of the lesson. Let me know if you guys have any questions. Thank you guys for watching.